So now we're in a position to generalize the idea of lines and planes into higher dimensions. And that might sound mysterious, but there's nothing magical going on. If you think about it, I'll just pop back up to this example. Here we've got a line in R3. The first time you ever encounter lines, though, is usually in R2 in the Cartesian plane, right? When you're studying slope-intercept form of the equation or point slope form and so on. You know, like when you write your lines as y equals mx plus b and whatnot. You first encounter lines in R2 because that's the most natural place to introduce them. But it also makes sense to draw them in R3 as well. When we talk about planes, well, if you try to draw a plane in two dimensions, in two-dimensional space, the only plane that you can draw is all of R2, right? You get, as soon as you have a plane in R2, you automatically have everything. You have all of R2. That's the only plane in R2, is R2 itself. So usually the first time you start drawing planes is in three dimensions. That's a natural place to introduce planes. But in both cases, it really just comes down to dimension. So what's a line? It's a one-dimensional subspace of any Rn, right? And a plane is just a two-dimensional subspace of any Rn. So let's add that in now. So that's really your official definition of a line. So a line in Rn is just a subspace of Rn with dimension 1, and a plane in Rn is just a subspace of Rn with dimension 2. And I just want to make a comment too. There's another type of subspace that you can say in general for any Rn, and that's referred to as a hyperplane. Now, hyperplanes are not particularly exciting until you get up to at least Rn for n is greater than or equal to 4. That's the first time a hyperplane will give you anything other than simply a line or a plane. But a hyperplane in Rn is just a subspace of Rn with what you'll sometimes hear it called is has codimension 1. But in our case, the way we're just going to say it is just has dimension n minus 1. Codimension 1 means it's one dimension less than the whole space. So a more straightforward way to say that would just be to say, okay, it has dimension n minus 1. So that's what a hyperplane is. So in the case of R3, a hyperplane is a two-dimensional subspace. Well, that's the same as a plane. And in R2, a hyperplane would be a one-dimensional subspace, which is just a line. But as soon as you get to R4, well, then a hyperplane is now a three-dimensional subspace of R4, so that's markedly distinct from either a line or a plane. Now, how do you draw them? Well, if you figure it out, let me know, because now you're getting into a situation where you're trying to draw four-dimensional spaces or higher, and that's something that I mean, maybe you can do it, but I certainly haven't found a way. Okay, so let's look at some more dimension examples. Remember the null space of a matrix. For any matrix, you can talk about the null space, which is just the set of all solutions to the associated homogeneous system. So the null space is a subspace. In particular, it's a subspace of Rn if your matrix A has n columns. So the dimension of the null space is referred to as the nullity. So we'll write it this way. The nullity of a subspace, or pardon me, a nullity of a matrix A is defined by the following. Nullity bracket A, so that's the notation for nullity, and all it is just the dimension of the null space of A. The main reason for this introduction here in this term is that quite often you have to talk about the dimension of the null space. But there's two sort of concepts that get mapped through here, the null space and then the dimension of the null space. So just to kind of cut down on that, we just have a shortcut term to just refer to that dimension. It's just the nullity. Okay, so for example, how do you find the nullity of a matrix? Well, find a basis for its null space and count the vectors. So here's an example. And if you haven't found a basis for a null space recently, or you've forgotten how to do that, here's a reminder. So here's a matrix A. We're going to find we're going to find a basis for the null space, and then we're going to count the vectors in that basis, and that's going to give us the nullity of this matrix A. So how do you find the nullity? Start with the augmented matrix of the associated homogeneous system, right? So take your matrix A to be the coefficient matrix of a linear system, and then just take the constant column to be the zero vector, or all zeros. And now you've got a linear system to solve. So do that, and when you solve it, what you're going to, when you row reduce it, this is what you're going to get. By the way, you could actually just start assigning parameters right here because you can tell what the pivot columns are going to be, right? You can tell that column 1 and column 2 is going to be a pivot column. So if you'd like, you could just assign parameters to whatever variable you want to introduce to associate with the second and fourth column, and then you could start solving for your basic variables that way. But I just personally, as a matter of personal choice, I like to go all the way to reduced row echelon form because then that way, once I assign my parameters, I won't have a bunch of algebraic operations to worry about. It'll be fairly straightforward to write down the general solution, but there's a cost. Then the cost is hidden here because I've glossed over the extra row operations that are involved. But nonetheless, this is another option that you have, is just to carry it all the way to reduced row echelon form every time, which is my personal preference. So that's what I've chosen to do here. Okay, so this is what you get if you row reduce to a matrix. All you have to do is just multiply row 2 by -1, and then subtract row 2 from row 1 4 times to get rid of that 4. And then lastly, you'll want to multiply row 1 by a half to turn that 2 into a 1. And then that'll bring you to this. Okay, so there's nothing magical going on there, just a few row operations. But now we're going to write down the general solution. So let's assign some variables to these columns. Let's say x1, x2, x3, and x4, like that. So then you can see that, okay, x1 and x3, those are going to be your basic variables, but x2 and x4, you're going to assign parameters to those variables. So let's do that. So I'll say x4 is going to be s, then I'll say x3 is going to be 7s, x2 will be t, and then x1 will be, what do we get if we write out the equation for x1? We'll end up getting x1 minus 3/2 x2 plus 15x4 is equal to 0. So if you isolate x1, you're going to get, on the other half of your equation, you're going to get 3/2 x2 minus 15x4. But once I plug the parameters in, I'll have 3/2 t, because x2 is equal to t, minus 15s, since x4 is equal to s. So that's how I get my general solution. So let's put it together into column form, like we typically do. So x1, x2, x3, x4. So that, is equal to what? So we'll have 3/2 t minus 15s for x1. Then we've got t for x2, 7s for x3, and s for x4. So we're going to split this up in the usual way. So we'll have 3/2 t 0, 0 plus what? Negative 15s 0, 7s, s. Okay, and then now I'm going to pull out now what do we normally do here? Typically we just pull out a t, and then we'll have 3/2 1, 0, 0. Now you can do that, but what you'll often see people do is they'll do something like this. I'll pull out, rather than just pull out a t, I'll pull out t over 2. And what difference will that make? Well, now I'll end up with 3 for the first entry, then I'll have 2 for the second entry, and then 0, 0. So notice I don't have any fractions now. Okay, but this still works for what I want to do. I'm still trying to obtain basis vectors for the null space, so I'll still get basis vectors this way. They'll just be scaled. They'll have maybe a different scaling. In this case, my basis vector 3, 2, 0, 0 will be twice as long as it would have been if I had just pulled out a t, and I would have got 3/2 1, 0, 0. But let's keep going. So now I'm going to pull out the s, and I'm just going to pull out s this time because there's no fractions to worry about. So I'm not gaining anything by pulling out a fraction or trying to pull out anything creative. But I'll end up with this negative 15, 0, 7, and 1. Okay, so that means we have these vectors here. I'm not scribbling them out. It looks like I'm scribbling them out. These vectors here will be our basis vectors for the null space. So let's formulate that down here. So B is going to be a set containing 2 vectors, 3, 2, 0, 0. And this is where it's nice to not have to write fractions. So negative 15, 0, 7, 1. So that set consisting of those 2 vectors is a basis for the null space of A. So we can now say, therefore, the nullity of A is just the dimension of the null space. And since our basis had two vectors, the dimension of the null space is 2. So that's how we can find the nullity. So it just amounts to finding a basis for the null space and counting your vectors. Okay. Another idea, we've talked about two spaces now that are two subspaces you can associate with any matrix, the null space and then actually the column space, if you remember from the previous section. But we can also talk about something called the row space, and the concept is the same. Remember how the column space is just take the span of the columns? Well, for the row space, you're just going to take the span of the rows. So let's say I had an m by n matrix A, and I've written it precisely here so that it is a column of rows. So you could see some notation for each of the rows. Row 1 is A1, row 2 is A2, all the way down to the mth row, which is AM. And let's say we have that. Well, then the row space, where's my pen? So the row space of the matrix A is just the span of the rows. So we'll just say row space of A is equal to the span of the rows, A1, A2, all the way up to AM. Okay, and one of the interesting things, like we could have done something different. There's another way we could have defined the row space of A. We could have just defined it to be the column space of A transpose, since the columns of A transpose would be the same as the rows of A. So that's a way you'll see it defined in some places. The row space of a matrix is just the column space of its transpose. And so, but the fact that that works, it's worth pointing out that based on the way we've defined it, it gives you the same thing, but it's worth making the observation that the row space of a matrix A and the column space of A transpose, those are the same subspaces. Okay, so for any m by n matrix A, the row space of A and the column space of A transpose are equivalent. So let's just, it doesn't take much to do a really quick example. Let's say I had A to be, let's just keep it simple, 2 by 2. So I'll say 1, 4, 3, 2. Then what's A transpose? It would be 1, 4 for the first row, and then 3, 2 for the second row. Okay, so the row space of A would be the span, oh, I didn't leave myself much room here, be the span of what? Well, the first vector would be the first row of A, 1, 3, and then the second vector would be 4, 2, the second row of A. That kind of wrapped over to the second line. But the column space of A transpose, oops, well, that would be the span of what? Well, A transpose, the first column is 1, 3. And the second column would be, well, 4, 2. That's why I like writing column vectors better than row vectors, because they fit into space more naturally. Let me just draw this line here, so or this curve, just to isolate that example from everything else. So notice that in this case, the row space, you just considered the two rows of A. And so the row space of A was the span of those two rows. Well, the vectors, if you forget about the fact that they're represented as rows, the first vector is 1, 3, a two-dimensional vector, and the second vector is 4, 2, another two-dimensional vector. But if you look at the column space of A transpose, well, you're going to look at the two columns, and you can see those are just the same two vectors. They're just written as column vectors instead. Well, the fact that we write them as column vectors instead of row vectors doesn't change the essence of the space, right? So it just changes the notation that we ended up using. But so that's just an example to illustrate the fact that in general, row space and the column space of A transpose, sorry, let me start that over. The row space of a matrix A and the column space of the transpose of that matrix A are always going to give you the same subspace. And it's the same thing as if I look at the column space of A, I could say that's the same as the row space of A transpose. That's the kind of the dual version of this statement that we made.